Hello everyone, so today's video will be about determining the stability of DNA-based nanoswitches using urea titration. Now, in order to do this experiment, you're going to need a DNA nanoswitch that has a stem-like configuration, as we could see in this diagram here. And this is important because at each extremity, you're going to have a quencher and a fluorophore. And in the folded state of the DNA nanoswitch, the quencher is going to inhibit the fluorophore. But once we add the urea, it's going to go into an unfolded state, and then now the fluorophore is going to be able to shine. So in our situation here, we used BHQ1 as a quencher and 6-FAM as a fluorophore. Next, we're going to have to prepare our solutions. So there's two solutions that we're going to need to prepare. A first of urea containing our DNA nanoswitch, which this is the solution that you're going to add to the cuvettes. And then a second solution, which is a buffer solution, which also contains the DNA nanoswitch. And this mix is going to be added to the cuvettes to dilute the urea. So in order to prepare a urea solution, you're going to need the proper mass ratio of urea to water. So as you can see on the slide here, the mass of urea versus the mass of water has to have a ratio of 1.103. So for example, we used a solution that was at 10 molar. So we used 1.103 grams of urea for 1 gram of water. Now, it's important to keep in mind that we don't want to dilute the concentration of the DNA nanoswitch and only the concentration of the urea. So in order to do this, we have to make sure that both solutions, the original one of urea and the buffer that's going to dilute the urea, have to contain the DNA nanoswitch. So in our situation, we used a concentration of 30 nanomolar of DNA nanoswitch in each solution. Mixing urea with water creates an endothermic reaction, which means that it's very cold. And so in order to dissolve your urea properly, you're going to need to rotate between using a vortex and submerging the tube in a hot water bath in order to heat up the tube and dissolve the urea. In order to carry out our experiment, we used a Carry Eclipse fluorescence spectrometer. So essentially, this is a big machine that's going to be able to measure the fluorescence emissions of our fluorophore when it's separated by the quencher due to the urea concentrations. The next step would be to set up the parameters of your experience depending on what fluorophore you're using. I wanted to include an example of a urea dilution protocol. So here we could see that we have the concentrations of urea that is theoretical and practical. So theoretically, we'd start at 10 molar and we'd end at 0. But because of the concentrations that we made in our solutions, it varies a little bit. And then at the end here, we have the volume of DNA in buffer that's added. And basically, it's just a way to keep track of what concentration you're at and what volumes of DNA in buffer need to be added to obtain these concentrations. And when you've managed to measure the fluorescence at each urea concentration that you decided, you're now going to be able to make a graph of the fluorescence versus the urea concentration, and it should look something like this. Now, in order to know the stability of our DNA nanoswitch, we need to know the value of the delta G. So using an equation, as we could see here, you're going to be able to fit the results you obtained previously with this equation to now obtain the delta G. Using your program of choice, you're going to be able to obtain your delta G value, which in our case, we used Kalidograph. So this is how our results were presented. So as we could see, our delta G for this specific DNA nanoswitch was a negative 2,835 calories per mole. Now, using the Gibbs equation, we're going to be able to put our delta G value into the equation to now get our value of switching constant. And this information is going to tell us if the DNA nanoswitch prefers to stay in a folded state or in a unfolded state. Lastly, I just wanted to show you that this protocol is applicable to all sorts of different situations. If you wish to have more details about the experiments and the equations that we used, feel free to consult our article for more information. And thanks for listening.